Hi there, let's discuss section 21.3 on alpha levels. In the previous few videos, we discussed hypothesis tests, either for a proportion or a mean, depending on the type of variable we were working with. And we noticed that when the p-value is small, we reject the null hypothesis. The question is, how small is small? Your idea of a small p-value may be different from my idea of a small p-value. So that's the question we'd like to investigate in this section. Recall, when the p-value is small, it tells us that our data from the sample are rare given the null hypothesis. So a p-value is a conditional probability. It's the probability of the observed statistic value, or one even more extreme, given the null hypothesis. So as I said, we want to decide how small is small or how rare is rare. We can set an arbitrary threshold for our p-value, and we call this an alpha level or a significance level, and we denote it by alpha. If our p-value falls below alpha, we reject the null hypothesis. We call such results statistically significant. Common alpha levels are 0.1, 0.05, 0.01, and 0.001. Now it's important to choose an appropriate alpha level for the situation. And you want to do this before you look at the data. Don't fall into the trap of not even thinking about an appropriate alpha level before you start looking at the data. Those of you that play tennis may be able to relate to this next exercise. It's called racket spinning. Tennis players often spin a racket on its end to observe whether it lands with the handle's label facing up or down as a random method for determining who serves first in a game. Suppose you were to spin the racket 200 times. We want to see if the handle's label lands facing up or down. The goal is to determine whether or not sample data provide evidence that the proportion of up results would differ from 0.5 in the long run. So let's set up a hypothesis test. The null hypothesis is that p, the true proportion, is equal to 0.5. In other words, there's no reason to believe that the proportion of up results should differ from the proportion of down results. The alternative hypothesis is that p is not equal to 0.5, that in fact the up results, or the proportion of up results, does differ from the proportion of down results. This is a two-sided or two-tailed alternative, since we're specifying that p is not equal to the hypothesized value of 0.5. So let's do this. Let's consider some different sample proportions. In this first part, let's suppose the number of up results is 113. Then our sample proportion would be 113 out of 200, or 0.565. We'll calculate a test statistic. In this case, it's a z-score. We take our observed proportion p hat minus the hypothesized proportion p0, that comes from the null hypothesis, and in this case is 0.5, over the standard deviation of p hat. So I've got the calculation for the standard deviation shown below. Here's that calculation. The standard deviation of the sampling distribution of the proportion is equal to the square root of p naught q naught over n, where p naught is the hypothesized proportion, 0.5, q naught is 1 minus p naught, and n is the sample size. So this gives us 0.0354. And that allows us to finish our calculation for the z-score. We get a z-score of 1.84. So to find our p-value, we'll start by looking up this z-score in the table. And because it reports area to the left, I'll subtract from 1 to get 0.0329. And because this is a two-sided or two-tailed alternative, we need to double this value, and that gives us 0.0658. Now, is this significant at an alpha level of 0.05? No, it's not, because our p-value is greater than 0.05, so we'll answer no. For part B, let's suppose the number of up results is 115. Then our sample proportion is 115 out of 200, or 0.575. Our z-score is found by taking the sample proportion minus the hypothesized proportion over the standard deviation of the sampling distribution, and this gives us c equals 2.12. So our p-value ends up being 0.034, and because this is less than 0.05, we say this is significant at an alpha level of 0.05. In part C, we'll suppose the number of up results is 130, giving us a sample proportion of 0.65. Our z-score would be 4.24, and this tells us the p-value is essentially 0. And again, this would be significant at an alpha level of 0.05. So in part D, notice the sample results are most similar in parts A and B, where you had very close to the same number of ups. In fact, we had 113 up results in part A and 115 up results in part B. So that's only a difference of 2. But notice in part A, we concluded that this was not significant at an alpha level of 0.05, whereas it was significant in part B. What I'd like to point out in part E is that the test decisions are the same in parts B and C, even though the sample results are quite dissimilar. In part B, we had 115 up results. In part C, we had 130 up results. So there's much greater spread between these two, but we said each were significant at an alpha level of 0.05. The moral of the story is this: it is unwise to treat standard significance levels as sacred. There is no sharp border between significant and insignificant, only increasingly strong evidence as the p-value decreases. For this reason, reports of significance tests should include the sample information and p-value, not just a statement of statistical significance or a decision about rejecting a hypothesis.